Greetings, everybody. Learning as a hobby here. I want to, in this video, go through my summary for Chapter 7 in Spivak. So let me bring up the notes and we'll go through it. It's a relatively quick chapter. I'll explain why when I bring up the notes. Okay, so Chapter 7 in Spivak is basically, he's using this to motivate what we're going to do in Chapter 8, which is going over the least upper bound property for the real numbers, which is a property that we haven't looked at yet. It's not a property that follows from the ordered field axioms that we had in chapter 1. So it's a new property, and he's motivating that with chapter 7. So the things we're going to do in here, specifically the three theorems that the chapter starts with, which he calls three hard theorems, all rely on the least upper bound property of the real numbers. So they're not proven in this chapter, but he gives them to us here at the beginning of chapter 7, and then we use those theorems to prove a bunch of related results in the rest of the chapter. So, and then the problems in the exercise set also, I would assume, I haven't done them yet, but I would assume rely on these theorems as well. So let's go ahead and just talk about, just read through what the theorems are first, and then we'll look at the theorems that he uses, the theorems that he proves using these three theorems. We'll look at those in a minute. All right, so here's theorem 1. If f is continuous on the closed interval from a to b, and f of a is less than 0, is less than f of b, then there's some x in the closed interval from a to b such that f of x is equal to 0. Okay, so that's, if you remember back to your pre-calculus and your calc 1, this is like a special case of the intermediate value theorem. And like I said, he doesn't prove this in the book in chapter 7 because we need the stuff we're going to do in chapter 8 in order to do that. So we'll prove this theorem in chapter 8. Here's theorem 2. If f is continuous on the closed interval from a to b, then f is bounded above on the closed interval from a to b. That is, there is some number n such that f of x is less than or equal to n for all x in the closed interval from a to b. Right, so continuous functions defined on closed bounded intervals are bounded above. Right, and then here's theorem 3, the last of the big three theorems in this chapter. If f is continuous on the closed interval from a to b, then there's some number y in the closed interval from a to b such that f of y is greater than or equal to f of x for all x in the closed interval from a to b. What this is saying is that continuous functions defined on closed bounded intervals take on their maximum value in that interval, over that interval. Okay, so with those three theorems, we're going to use them, like I said, to prove a bunch of related things. So we'll just go through them one at a time. The first few, their proofs are pretty straightforward and short because they rely almost directly from the theorems that we just looked at. Here's theorem 4. If f is continuous on the closed interval from a to b and f of a is less than c is less than f of b, then there's some x in the closed interval from a to b such that f of x is equal to c. And the proof, like I said, follows directly from theorem 1. So what we do first is we define a new function, we call it g of x, and we define that to be f of x minus c. All right, then if you subtract c from all three sides of the inequality up here, you get g of a is less than 0 is less than g of b. So by theorem 7.1, there exists an x tilde in the interval from a to b such that g of x tilde is 0, which implies that f of x tilde minus c is 0, or in other words, f of x tilde is c. So that proves theorem 4. Like I said, it follows pretty directly from theorem 1. And same idea, similar idea for theorem 5 here. If f is continuous on the closed bounded interval from a to b, then f of a is greater than c greater than f of b. Sorry, and f of a greater than c greater than f of b, then there's some x in the closed interval from a to b such that f of x is equal to c. Right, similar type of idea behind the proof here. Define g of x to be the negative f of x, then g of a is less than c is less than g of b, which implies there's an x tilde in the interval from a to b, such that g of x tilde is minus c, which implies negative f of x tilde is negative c, or in other words, f of x tilde is c. So again, just follows directly from actually what we did in theorem 4. So right. I should say there's just as usual with Spivak, there's a lot of conversation that takes place in the chapter where he gives you like, some nice intuitive explanations of things, and also he has some really nice graphs and stuff that illustrate the concepts here. So you should take some time and actually read through the chapter yourself. As always, my chapter summaries are just that. They're just skeletons of the chapter. So I just basically take all the salient points and just summarize everything. But there's a lot more in the chapter that you should read. So anyway, he does make a note here. Theorem 4 and 5 imply that if f is continuous on the closed interval from a to b, then for any cd, a number cd in the interval from a to b, where c is less than d, then f takes on all values between f of c and f of, sorry, this should be f of c and f of d. There should be a d here. And now my computer's going to freeze. So I just give it a second. Okay, so here, this should be a f of d. Oh, is it? Okay, thought it froze again. Okay, this is called the intermediate value theorem, if you remember from pre-calculus or from Calc 1. You should have learned that there. Okay, here's another theorem, theorem 6. If f is continuous on the closed interval from a to b, then f is bounded below on the closed interval from a to b. That is, there is some number n such that f of x greater than equal to n for all x in the closed interval from a to b. So again, this follows directly from theorem 2 in this case, and similar type of trick that we had for the previous couple theorems. Define g to be the function negative f, then g is continuous on the closed interval from a to b, and there's a number n such that g of x is less than equal to n for all x in the closed interval from a to b. That's from theorem 2. Then negative g of x equals f of x is greater than or equal to negative n for all x in the closed interval from a to b, and that proves the theorem. All right. Hopefully these are, seeming pretty straightforward. He says here also, theorem 2 and 6 show that a continuous function on a closed interval is bounded. In other words, f continuous on the closed interval from a to b implies there exists a number n greater than or equal to 0, such that the absolute value of f of x less than equal to n for all x in the closed interval from a to b. In fact, since you can find a number n2 and a number n1 such that n2 is less than equal f of x less than equal n1 for all x in the closed interval from a to b. We take n equal to max absolute value n1, absolute value n2, and that will work. That's an a value that you can use as an upper bound for the magnitude of f. All right. Going on to theorem 7, if f is continuous on the closed interval from a to b, then there's some y in the closed interval from a to b, such that f of y is less than equal to f of x for all x in the closed interval from a to b. This one is going to follow directly from theorem 3. He says a little note here too. A continuous function on a closed interval takes on its minimum value in that interval, just like theorem 3 says that a continuous function on a closed interval takes on its maximum value as well on that interval. Only here we're talking about minimums instead of maximums. All right. And it looks like for some reason the Jamboard erased some of my letters here. I don't know why I did that, but let me just fix that. Okay, so here's the proof. Define g equal to negative f, then g is continuous on the closed interval from a to b, and there is an x in the interval from a to b such that g of x is greater than or equal to g of y for all y in the interval from a to b. Then negative f of x greater than or equal to negative f of y implies f of x less than or equal to f of y for all y in the in the closed interval from A to B. Okay, so wait a second, did I do this? There's an x in the interval from A to B such that g of x. Oh, I see. I switched the variables around. This works fine. It's just here the fixed value is x, not y. Sorry, I just got threw off by that because he uses f and y, sorry, x and y in the reverse order here. But this is fine. It's just I just swapped the x's and y's here. All right, theorem 8. Theorem 8 says every positive number has a square root. In other words, if a is greater than 0, then there's some number x such that x squared is equal to a. Right. So again, this follows directly from the theorems that we looked at. So here, let a greater than 0. Define f of x equal to x squared minus a. Then f is continuous on R. And notice that f of 1/2 a is less than 0 is less than f of 2a. And that implies that there's an x in the real numbers such that f of x equals x squared minus a equals 0. Therefore, x squared equals a. So every real number has a square root. Sorry, every positive real number has a square root. Okay, in fact, this result can be generalized to the statement that any positive number has an even nth root. It's even better for odd roots, which we'll see in a second. Every real number has an odd nth root, which we're going to prove in theorem 9. So here, if, well, actually, not specifically, we're going to show that every odd degree polynomial has at least one real root. So anyway, here we go. Theorem 9. If n is odd, then any equation x to the n plus a n minus 1 times x to the n minus 1 plus dot 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 plus a0 equals 0 has a root. And here's the proof. This is kind of a complicated setup that he has here, but we'll go through it carefully a little bit at a time. So here let n be odd, then x to the n plus a to the n minus 1 times x to the n minus 1 plus dot 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 plus a0. You can rewrite that over like this by just factoring out the x to the n from all of the terms here. So that's equal to x to the n times 1 plus a to the n minus 1 over x plus dot 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 plus a0 over x to the n. Then what we do is we choose x so that the magnitude of x is greater than or equal to 1 or 2 to the n times absolute value a n minus 1, 2 to the n a n minus 2, dot 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 down to 2n absolute value a0. So we want to choose the magnitude of x so large so that it's bigger than each of these numbers here. Okay. And then so since the magnitude of x is bigger than 1, x to the k is greater than or equal to absolute value x. And then if we take reciprocals, the inequality direction switches. So 1 over absolute value x to the k less than or equal to 1 over absolute value x. And then here that implies that, so if we just multiply through here by the absolute value a to the k minus 1, we get that absolute value a to the k minus 1 over absolute value x to the k is less than or equal to absolute value a k minus 1 over absolute value x, which is less than or equal to absolute value a to the n minus 1, or sorry, k minus 1 over 2n absolute value a to the k minus 1. And notice that these cancel here. And you're left with just 1 over 2 to the n. And these inequalities here follow from this fact here, that we let x be big in magnitude be bigger than these numbers. All right, then from that we get that the absolute value of a n minus 1 over x plus dot 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 plus a0 over x to the n is less than or equal to, by the triangle inequality, the absolute value of each of the terms, which by what we just derived above is less than or equal to 1 over n summed with itself n times, which simplifies to give you 1/2. And then just turning the absolute value inequality here into its equivalent compound inequality, that's the same thing as saying negative 1/2 is less than or equal to a n minus 1 over x plus dot 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 plus a0 over x to the n less than or equal to 1/2. And if you add 1 to all three sides of the inequality here, you get 1/2 is less than or equal to 1 plus a to the n minus 1 over x plus dot 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 down to a0 over xn. And now finally we have what we need in order to do this. So choose x1, x2 in the real numbers such that the absolute value of each of those numbers is greater than the the numbers that we wanted up above. And choose x1 to be positive and x2 to be negative. All right, then from this inequality here, if we multiply through by x1 to the n over 2, this number is positive because x1 was positive, right? We picked this to be positive, which is, and also x1 is greater than these numbers here in magnitude. So, just multiply x to the 1 to the n times both sides of this inequality here. You get this, which shows that this number here is positive. And then if you do the same thing for x2, which is here we chose x2 to be negative, but with magnitude bigger than these numbers. So here you multiply x2, sorry, I'm getting tongue-tied here. You multiply by x2 to the n on both sides of the inequality here, but since x2 to the n is negative and we're raising that to an odd power, x2 to the nth power is negative, so we have to switch the direction of the inequality, which gives us the second line here, and x2 to the n over 2 is less than 0. We just said that because it's negative, which is less than or equal to this expression by this inequality here. So we get that this number is negative. Okay. Therefore, f of x equals x to the n plus a n minus 1, x to the n minus 1 plus dot 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 plus a0 satisfies this inequality here. F of x2, note it from what we just derived above, is less than 0, and f of x1 is greater than 0. And f is continuous on the closed interval from x2 to x1 because it's a polynomial. Therefore, there exists an x in the closed interval from x2 to x1 such that f of x is equal to 0 by theorem 1. Okay, so that's kind of a involved proof, but really just all that complicated stuff is just needed in order to get an actual x2, x1 that works. All right, here's theorem 10, which is says something about even degree polynomials. If n is even and f of x equals x to the n plus a n minus 1 times x to the n minus 1 plus dot 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 plus a0, then there's a number y such that f of y less than or equal to f of x for all x. Right, so here we're going to actually use the same inequality that we derived from the previous theorem. Let m be the maximum of these numbers here, 1 to n absolute value at n minus 1, comma dot 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 down to 2n absolute value a0. Then we know that this inequality holds. We already derived that up above. Choose b to be a positive number such that b to the n is greater than or equal to 2f0, and b is greater than m, and choose x to be greater than or equal to b. All right, then f of 0, but by this fact here, f of 0 is less than or equal to b to the n over 2, which is less than or equal to x to the n over 2 by this inequality here, and that's less than or equal to f of x by the inequality that we have up here. Right. Also, if we choose x to be less than negative b, then we get the same thing because n is an even power. When you raise a negative number to an even power, you get positive a positive number from that. So the same inequality holds for negative b. Then for all x, where x is less than or equal to negative b, or x is greater than b, we have that f of x is greater than or equal to f of 0. Also, by theorem 7, there is a y in the closed interval from negative b to b, such that for all x in the interval from negative b to b, f of y is less than or equal to f of x. That follows directly just from theorem 7. Then, since 0 is in the interval from negative b to b, that implies that f of y is less than or equal to f of 0. Therefore, f of y is less than or equal to f of 0 less than or equal to f of x. So that means that f of y is less than all f of x for no matter what x is. So for any x, and we broke the domain up into these three intervals, but if you take the union, you get the entire real line. So you get the actual minimum for the function. Right. So again, kind of a complicated construction. That's just to be able to say that, to sort of like zoom in on the actual global minimum of the function instead of like getting stuck at like a local minimum or something. All right, here's the last theorem in the section, or sorry, in the chapter. Theorem 11, consider the equation x to the n plus an minus 1 times x to the n minus 1 plus dot 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 plus a0 equals c. And suppose that n is even, then there's a number m such that this equation here has a solution for c greater than or equal to m and has no solution for c less than m. Right, and this one is relatively straightforward compared to the last two that we did, but here we go. By theorem 10, there is a y in the real numbers such that f of y less than equal to f of x for all x in R. Let m equal f of y. Then if c is less than that minimum value, then f of x is always greater than c, which means that for all x, which means that there's no solution to the equation f of x equals 0 in that case. Oh, sorry, f of x equals, should be f of x equals c in that case. If c is equal to m, then y makes f of y equal to c. Therefore, y is a solution to the equation. And lastly, if c is greater than m, then choose b so that b is greater than y, and f of b is greater than c. Then f of y, which is equal to m, is less than c less than f of b, implies there's an x in the closed interval from y to b, such that f of x equals c, or c just by theorem 4. It just follows directly from theorem 4. So that shows the theorem 11 holds. And then there's just one last little bit that I want to talk about, and then the next video will be on the solutions to some of the selected exercises from chapter 7. So he ends the chapter with talking a little bit about what we're going to do in the next chapter. So the proofs of theorem 1, 2, and 3 require a property of the real numbers that's not possible to prove from the ordered field axioms that we learned in chapter 1. So we'll study this property in the next chapter. The property is called the least upper bound principle. The real numbers are an ordered field that satisfies the least upper bound property. So we'll look at that in chapter 8. Let me stop the screen share for a second. I apologize for my voice. I think I might be getting sick or something. What was I going to say? Oh, the next video will be selected solutions to the exercise set for chapter 7. Let me know what you guys think in the comments down below. And I'll see you guys in the next video. Please do like and subscribe if you enjoy the content. And take a look at the Patreon page. It's $5 a month and there's extra content on there. And I'll see you guys in the next video. All right, keep learning for now, everyone.